There is extensive research indicating some probable increased risk of cancer, particularly lung cancer, from inhaling fumes while welding stainless steel. Stainless steel welding is suspected of producing carcinogenic fumes from cadmium oxides, nickel, and chromium. According to Cancer Council Australia, in 2017, all types of welding fumes were classified as a Group 1 carcinogen. Stainless steel is generally considered to be biologically inert. However, during cooking, small amounts of nickel and chromium leach out of new stainless steel cookware into highly acidic food. Nickel can contribute to cancer risks, particularly lung cancer and nasal cancer. However, no connection between stainless steel cookware and cancer has been established. Stainless steel is an alloy of iron that is resistant to rusting and corrosion. It contains at least 11% chromium and may contain elements such as carbon, other nonmetals and metals to obtain other desired properties. Stainless steel's resistance to corrosion results from the chromium, which forms a passive film that can protect the material and self-heal in the presence of oxygen. The alloy's properties, such as luster and resistance to corrosion, are useful in many applications. Stainless steel can be rolled into sheets, plates, bars, wire, and tubing. These can be used in cookware, cutlery, surgical instruments, major appliances, vehicles, construction material in large buildings, industrial equipment e.g., in paper mills, chemical plants, water treatment, and storage tanks and tankers for chemicals and food products. The biological cleanability of stainless steel is superior to both aluminium and copper, having a biological cleanability comparable to glass. Its cleanability, strength, and corrosion resistance have prompted the use of stainless steel in pharmaceutical and food processing plants. Different types of stainless steel are labeled with an IC 3-digit number. The ISO 15510 standard lists the chemical compositions of stainless steels of the specifications in existing ISO, ASTM, N, Gs, and GB standards in a useful interchange table. The invention of stainless steel followed a series of scientific developments, starting in 1798 when chromium was first shown to the French Academy by Louis Vauquelin. In the early 1800s, British scientists James Stoddard, Michael Faraday, and Robert Mallet observed the resistance of chromium-iron alloys to oxidizing agents. Robert Bunsen discovered chromium's resistance to strong acids. The corrosion resistance of iron-chromium alloys may have been first recognized in 1821 by Pierre Berthier, who noted their resistance against attack by some acids and suggested their use in cutlery. Unlike carbon steel, stainless steels do not suffer uniform corrosion when exposed to wet environments. Unprotected carbon steel rusts readily when exposed to a combination of air and moisture. The resulting iron oxide surface layer is porous and fragile. In addition, as iron oxide occupies a larger volume than the original steel, this layer expands and tends to flake and fall away, exposing the underlying steel to further attack. In comparison, stainless steels contain sufficient chromium to undergo passivation, spontaneously forming a microscopically thin inert surface film of chromium oxide by reaction with the oxygen in the air and even the small amount of dissolved oxygen in the water. This passive film prevents further corrosion by blocking oxygen diffusion to the steel surface and thus prevents corrosion from spreading into the bulk of the metal. This film is self-repairing, even when scratched or temporarily disturbed by an upset condition in the environment that exceeds the inherent corrosion resistance of that grade. The resistance of this film to corrosion depends upon the chemical composition of the stainless steel, chiefly the chromium content. It is customary to distinguish between four forms of corrosion: uniform, localized pitting, galvanic, and SCC, stress corrosion cracking. Any of these forms of corrosion can occur when the grade of stainless steel is not suited for the working environment. Stainless steel is used in a multitude of fields including architecture, art, chemical engineering, food and beverage manufacture, vehicles, medicine, energy and firearms. Stainless steel nanoparticles have been produced in the laboratory. These may have applications as additives for high-performance applications. For example, sulfurization, phosphorization, and nitridation treatments to produce nanoscale stainless steel-based catalysts could enhance the electrocatalytic performance of stainless steel for water splitting.